What's one simple thing that I can do to figure out whether or not one thing is better than the other? Well, we have electroscopes. Okay, so we take a material, any two materials, and we rub them next to each other, and we find out whether or not one's stronger than the other by does it have an excess charge. For example, I could take this metal pair of scissors and my arm here, all right, and rub them next to each other, okay, and make a prediction. I can make a prediction. Now you'll notice I've got an insulated handle right here, so I shouldn't be losing any charge, all right? If I put that on there, nope, absolutely no effect whatsoever. What does that mean? Roughly, they hold on about the same. One is about the same amount of electrons as others. Okay. Now the balloon and hair, more than likely, based on what we just saw, yeah, definitely has a charge in that particular case. Now the set of materials that we have used, the rubber rod and the fur and the glass rod and the felt and the silk, are known quantities. Those are probably some of the best that we have. But you can take any sets of materials. You could take your clothes. You could take your clothes and put it on your skin and go like this. Put it on there. See, probably not very much for this set of clothes. Now, depending on what set of clothes you're using, this is going to be different. For example, if you're wearing athletic shorts, particularly on a cold day, you might find usually you have to deal with some type of static in that particular case. Why? Athletic shorts are particularly bad at holding on to electrons. So they lose electrons to your hair all the time, and then they get charge on your pants. And what does the charged pants do to your leg? Exactly what you just saw with the balloon. It rearranges the charges in your leg so that the opposite charge is nearby and it sticks to you in that particular case. Or those of you that are combing your hair in the morning, talking about friction. This is perfect for the rubber rod and the fur. Specifically if you have lighter hair, particularly on a cold day. You rub your hair in the morning, specifically if you're doing it with a plastic comb. I know this is a lot of conditions. Okay, you do that, and you find out when you're done that your hair sticks up. Okay, well, what charge more than likely is your hair if it acts like the rubber rod and the fur? Positive. And what do positives do to other positives? Repel. So your hair repels early in the morning. Now those of us with thicker hair probably don't have to deal with that type of issue the same way as those with lighter hair, but it certainly is going to be possible. Now, what's the one solution that you have for that? Well, you could touch something that is metal, you could touch something that is grounded, or more than likely what you regularly do is you take water and you put water in your hair, and water donates electrons or takes away electrons so that you end up as neutral. And when you end up as neutral in that particular case, obviously there's no longer an attraction and you can go about your day. All right, a couple of quick slides. We're going to continue working on this, but I'll tell you, the practice of getting good at this chapter is thinking about these situations and trying to put it to terms of those basic rules that we started with. The basic rules that we started with, just a reminder, are these right here. Absolutely everything comes from these rules right here. Where does charge come from? It comes from the atom, electrons and protons. Charge is conserved. It always goes somewhere, it doesn't disappear. Which charges move? The electrons move. Why don't the protons move? Because they're in the nucleus, held on by the strong force. So positives repel, opposites attract, and then kind of by extension, I would say, what is the normal charge of macro objects? It's neutral because it's an equal number of positives and negatives. So how do you get something to be negative or positive? Something is negative if it has excess electrons, and positive if it is missing those particular electrons. All right. Quantization of charge. I'm just going to say this. Charge is quantized, but I'm going to let you read on what it is. Too many people do not read as we get into physics further, and so this is my heavy push to at least have one concept not discussed in here that you must read, that is very attainable when you read it carefully, but I will tell you that a lot of people get it wrong, what quantization actually means, so read carefully. Specifically on the Millikan oil drop. Okay, you can find that in the textbook, you can find that online. I would probably suggest your textbook, but that is up to you. All right, moving on. So here's a weird thing that we move into. We need to start being able to measure charge in the same way that we measure mass. What units do we use to measure mass? Kilograms, or if you're in chemistry, grams, typically, depending on how much you're particularly using. So if I said you had 3.2 kilograms, you would say this. You would say mass is equal to 3.2 kilograms. Okay? Charge's symbol is Q, and is measured in coulombs, abbreviated as capital C. This is a measure of how much charge is in an object. So if I said something, if I wanted to know the charge of, say, that balloon over there, I might say that the charge of the balloon is equal to 3.2 microcoulombs. I'm going to talk to you about that micro a little bit towards the end of today. Actually, I'll talk about towards the end of this slide. The main thing to get there is that that is in coulombs. Now, technically speaking, the base unit of mass is grams, and kilo is a SI unit that means times 10 to the third. Now, I say technically because actually it is in fact a kilogram, which is a little bit weird. Why isn't it just the gram? But in the same way, when I say charge, Q is equal to 3.2 microcoulombs, micro is an SI unit that means times 10 to the negative 6th. We are going to use a lot of SI units this chapter because it's going to make our lives easier, but we are going to have to get used to them. The major ones that you're going to need to get used to are ones that you know, milli times 10 to the negative third, micro, maybe a little bit less, negative 6, nano, negative 9, and pico, negative 12. Now, it does go beyond that, but those are going to be the main ones. So, the charge of an electron is set. The charge of an electron is negative 1.6 times 10 to the negative 19th. This is also known as negative E. I'll talk about why that in a second. Proton is exactly the same, except it's positive, which is a really good thing because now, because of that number being exactly the same, that's why if I have an equal number of negatives and positives, I would expect to have what charge? 0. Obviously, if they were imbalanced in this particular way, it would require more of one or the other in order to get back to 0. So, and positive E. Okay, little e here does not stand for, this is confusing and I apologize, it's what physics does. Okay, does not stand for electron. Does not stand for electron, it actually stands for elementary charge. Okay, the reason we use this little e right here is the exact same reason for a while I've been using G in calculations. Okay, what is G? 9.8. You already know what it is. And it's really nice to keep the G around in calculations so I don't have to write out 9.8 meters per second squared every single time I need to write it. I can just write G and all of you know what it is. It's the same thing with little e right here. Little e stands for this amount right here. And whether or not little e is negative or positive tells us that that is a proton or an electron. So let's talk about this. The number of electrons in a single coulomb, in 1 coulomb. Well, how could I figure that out? Relatively easily. Come back. Pen. Do I have options with a pen? Apparently not. Okay. So, how do I find this out? Well, I know the charge of 1 electron. So how many electrons are in 1 coulomb? It's actually, and you can do this with any amount, 1, 2, 3, however many coulombs. You could take the 3.2 microcoulombs and figure out how many electrons in it. Would there be a lot of electrons in a microcoulomb? Micro is negative 6. Should there be a lot of electrons in? I don't know. Do you consider billion, 10 billion to be a lot of something? Remember, this is times 10 to the negative 19th. Be careful when you get down to small numbers, because small numbers make you feel like, oh, everything is just small, so who cares? But is negative 6 quite as small as negative 19th? Absolutely not. Yeah. So this is, I think I misspoke a second ago. I think I said 13th. It's actually be to the 13th, right? So yeah, 12 is billion. Yeah, that's about right. Yeah, that would be like 10 billion, okay? But how much is in 1 coulomb? Very simple stuff here. We would just go, hey, actually I should technically make it, if it says electrons, I should technically make it negative. So a negative 1c, all I would do is multiply by, I know, in 1 electron, there is a charge of negative 1.6 times 10 to the negative 19th. So it's really just inverting that number. Someone punch that into your calculator for me real quick. My apologies. Red is not showing up super well here, is it? Let me try again.
6.25 times 10
So I'm going to say that's a decent amount of electrons. That is 1 million, sorry, that is 6.2 million billions. As we don't have as much context with the trillion and quintillion. That's why I decided to say not 6.25 quintillion electrons. All right, so because there's so much electrons, I will tell you, and I will show you proof of this a little bit later on, charges that you were dealing with in here today, okay, did not get to a Coulomb. To prove that, or to kind of give you context here, the amount of, and lightning bolts are definitely different, but the amount of charge in a single lightning bolt is about 10 coulombs, okay? So obviously you're thinking that's a lot of charge. It is a lot of charge, okay? A coulomb is an incredibly, incredibly, incredibly large amount of charge. So the amount of charge more than likely on this guy right now is probably in the microcoulombs. And we have methods of proving that we'll see a little bit later. So I'll just use context for it right now. I see it polarizing against the table. So I need to hold it out further so it doesn't polarize twice. Come on. Oh, darn. Prepped this better earlier. But the amount of charge that's causing, of course, negative and negative repulsion between the balloons right now is on the order of microcoulombs. Except I'll prove that a little bit later. All right, last slide. Electromagnetism depends on the amount of charge and the distance, which is very similar to another force that we have dealt with. What is that force that we've dealt with that also depends on the quantity of the thing as well as the distance? What other force that we have discussed, that we have an equation with, depends on how much the quantity the property has, as well as the distance between the two. I said, hey, there's two objects, right? Yes. Gravity, correct. So the equation has to account for that. So where should we put charge to account for that? Well, here we go. Let's call this force electric. Okay, how many charges does this depend upon? How many charges does it take to have a force? Two. Takes two, just the same way it takes two masses. So I should probably have charge 1 and charge 2. Where should charge 1 go in this equation? The top, the bottom, what do we think? Probably the top. Why does that make sense? What does this say if I put it on top? More charge means more force. Is that what you found? Like if I rubbed my head longer on one of these and got more charge on one of them, should there be a greater force? Okay, what about the second charge? Where should it go? Top or bottom? Top, very good, I like it. And what about the distance between them? How should that affect the force? Yeah, definitely on the bottom. The greater the distance, the smaller the amount of force, right? Now, you might remember this is a very similar setup to what I did previously, and I'll put, say, R on the bottom for distance. And I'd add a couple things to that, but let's just do it right there. Keep turning. Oh, stop. You're being difficult. Wait, no. Stop. Why can't I erase? That's fine. Electric force. Does that equation look very familiar to you? Not specifically, but does it look remarkably similar to another equation that we have already used? What equation is that similar to? Fundamental force of gravity is Fg. Can I write out here? No. Is equal to big G m1 m2 over r squared. This is equal to Kc, also known just by K. I'll regularly just write K up here. Okay, times Q1 times Q2 over r squared, where Kc is known as Coulomb's constant. It is 9 times 10 to the 9th. And similar, if you struggle with units, what units do we need over here? Well, we need newtons. What needs to cancel from the bottom? Meters squared needs to cancel, which means your distances do have to be in meters to use this equation, so meter squared is on top. And what units are Q in? coulombs, yeah, there you go. And so we have a c squared on the bottom to cancel with those two, so we are just left with newtons once we multiply everything out. Now, an important distinction between the force of gravity and the force electric, a couple of major things. Number one, you will remember we talked about the strength of them versus each other. And here's my simple example, and then I'll do a mathematical example, and then we'll be done for the day. Okay, here's the simple example. How much mass does it take to pull me down at my weight? What is the mass that is pulling me down at my weight right now? I stand on a scale, I look at that number. Well, how much mass does it take to pull that off? What object is pulling me down right now? Earth, the entire Earth. 5.98 times 10 to the 24th kilograms, a ridiculously large number. Do you know how many electrons it takes to counterbalance all of that mass pulling me down? The ones on the bottom of my shoe. So it takes all of Earth to pull me down, and it takes those electrons to entirely do the exact same amount of force up. Now, you guys are used to this force diagram, but it's just from a different perspective. That force diagram that I just gave you was, hey, force gravity is down. The Earth is pulling me down. All of the mass, 5.98 times 10 to the 24th kilograms, pulling me down. The electrons on the bottom of my shoe pushing me up. What do we usually call that? Force normal. And it results from charges on the bottom of my shoe at the distance. No, so obviously electrons do have that as an advantage. It's a much closer distance, but it just takes the electrons on the bottom of my shoe to pull that off. All right, I did the balloon example a second ago. We will do actually a little bit more with that balloon example tomorrow, but we are running out of time, so let's do this real quick. Force electric versus force gravity. I want you to use both equations, okay? I wrote this one up here just as a reminder, although I'll write it on the board because that's not great, okay? What is the force electric of the objects in a hydrogen atom? Meaning, a hydrogen atom has mass. There's the mass of the electron. There's the mass of the proton. Write those down. You are going to want to use those throughout the chapter. So if an object, if a problem tells you, it says, hey, you have an electron and a proton, immediately in your head, you should go to like the given. I have mass of both. I have charge of both. And if you forget either of those are on the AP equation sheet. Okay, so you never have to, I would keep that close to you with this chapter. So go ahead and calculate now using this equation what force electric is. And using this equation, go ahead and calculate what force gravity is. This is roughly where we will end today. Let me erase this. You're not going to let me erase that. Oh well. I don't know if I see all of you on the slide. You can do that.
What would we plug in for Q for
the charge? What is the charge of the electron?
just the positive?
Too far. Charge of the electron is 1.6 times 10 to the negative 19. Charge of the proton, positive 1.6 times 10 to the negative 19. Is the negative 19th important in this equation? Very much so, because we need to have this in coulombs. Okay?
Can we just write like negative E and positive E?
100%. As long as, obviously, when you punch that, that's the same, that's what I was trying to say with E, okay? You're welcome to write in negative and positive E when you do your writing, but obviously when you punch it in your calculator, you have to write 1.6 times 10 to the negative 19. Talking to some Physics 2 students over the years, specifically about electricity, I think their advice to you would be this: write it down for like the first, like until you know you have it memorized. Because this is a number that I don't require you memorizing anything, but as we did with like kinematics and stuff, there's certain ones that your life's going to be a lot easier if you just remember what it is. Does that make sense? So that's what they would probably tell you. Write it down as many times as is necessary until you're like, yeah, I don't need to write this down. I know. The same thing with G, right? Like when you were using G, I don't need to like ask. If I say, hey, what's G? Nobody in class is going to like look that up. Okay, please calculate those two numbers for tomorrow. That's where we'll be